technique that we're going to use to solve rational equations is called clearing the denominators. We can multiply both sides of an equation by a least common denominator to do what's called clearing the denominators, meaning after we multiply, there will be no fractions in our equation. You may have seen this technique for solving equations that contain fractional coefficients. As in this example, we have a linear equation with fractional coefficients. The denominators here are a 3, a 5, another 5, which I'm going to just write down again, and a 15, which is equal to 3 times 5. Looking at the factors here, my LCD is going to be a 3 times a 5 is 15. If I multiply both sides of this equation by 15, I claim I'm going to get something with all integer coefficients. So let's see how that works. We're going to say 15 over 1 multiplied by the left-hand side, 2/3 x minus 4/5 equals 15 over 1 multiplied by the right-hand side, 3/5 x plus 8/15. So I'll have 15 over 1 times 2/3 x minus 15 over 1 times 4/5 equals 15 over 1 times 3/5 x plus 15 over 1 times 8/15. Okay, so for illustration purposes, I'm now going to do this fraction arithmetic by hand. All right, 15 over 1 times 2/3. That's 15 times 2 over 3. 15 is 3 times 5. So I've got 3 times 5 times 2 over 3. Cancel the 3's. Notice the denominator canceled out. And I'm left with just 5 times 2 is 10. 15 over 1 times 4/5. That's 15 times 4 over 5. Again, 15 was 3 times 5. Cancel the 5's, and I'm left with just 3 times 4 is 12. 15 over 1 times 3/5. That's 15 times 3 over 5. Remember, 15 is still 3 times 5. Cancel the common 5's, and I'm left with just 3 times 3 is 9. And then 15 over 1 times 8/15. That's 15 times 8 over 15. Here I don't need to look at the factors. The 15's cancel directly, and I'm left with 8. So when I do this multiplication, I get the equation 10x minus 12 equals 9x plus 8. So I'll subtract 9x on both sides. X minus 12 equals 8. add 12 on both sides, and get x equals 20. Just to make sure that that really made sense, let's check that in the original equation. 2/3 times 20 minus 4/5. Just working out that arithmetic on a calculator is 188 over 15. 3/5 times 20 plus 8/15. Working that out on a calculator is also 188/15. Those are equal, so 20 really is a solution to that equation. And of course, that equation was a linear equation, so we know that that's the only solution. Okay, so that's the process of clearing denominators to solve a linear equation, really. That process lets us work with easier numbers in the solving process, but it wasn't really necessary. We could have solved that just by working with the fractions in the usual process for solving a linear equation. We'll use that same strategy, though, when we have variables in the denominators. So here we have a rational equation, x squared minus 10 over x squared equals 3 over x. We're thinking, I want to get rid of these denominators. So my denominators are x squared and x. Their least common multiple, so my least common denominator, well, I only have factors of x. The highest power is x squared. My least common denominator is going to be x squared. What happens then if I multiply both sides by x squared? On the left, I'll have x squared over 1 multiplied by x squared minus 10 over x squared. On the right, I'll have x squared over 1 multiplied by 3 over x. So I'll get, on the left, x squared times x squared minus 10 all over x squared. On the right, I'll get x squared times 3 all over x. On the left, the x squared factors cancel out. On the right, my x in the denominator cancels out, and I'll be left with x to the power 2 minus 1. Notice, everything in the denominators canceled out completely. After this step, after my multiply both sides by the LCD step, I have no denominators. So this gives me the equation. X squared minus 10 on the left. On the right, x times 3 is 3x. Right? This is no longer a rational equation. Now that I've cleared the denominators, I have a polynomial equation, which I know how to solve. So I have a polynomial equation of degree more than 1. Right? I've got an x squared in there. So I need to get 0 on one side. I'll subtract 3x on both sides. So I'll have x squared minus 3x minus 10 equals 0. And then the left-hand side, I'm going to try to factor. Let's see. Leading coefficient is 1, so I can use the shortcut. I need two numbers that multiply to negative 10. So one will be negative and one positive. I need them to add up to negative 3. I think the numbers that are going to work are a negative 5 and a positive 2. Okay, so that product is 0. One of the factors has to be 0. Either x minus 5 is 0, which gives me a solution x equals 5, or x plus 2 equals 0, which gives me a solution x equals negative 2. I claim that these two are the solutions to my original equation. My original equation was this: x squared minus 10 over x squared equals 3 over x. So to see if that really worked, I'm going to take each of these values and plug it into my original equation. I just grabbed a copy of the original equation and brought it down here so we can see it. And I'm going to try each of these numbers that I think is a solution. So I'm going to try x equals 5 in the original equation. That'll give me 5 squared minus 10 over 5 squared. So in the numerator, I get 15. In the denominator, I get 25. Simplifying that, I get 3. On the right-hand side, that's just 3 over 5. Those are equal. So 5 really is a solution. Next, I'm going to try plugging in x equals negative 2. So on the left, I'll have negative 2 squared minus 10 over negative 2 squared. That's going to be negative 6 over positive 4, which works out to negative 3/2. On the right, I'm going to have 3 over negative 2, which also works out to negative 3/2. Again, those are equal, so that really is a solution. Plugging in both x equals 5 and x equals negative 2 made my original equation true. So 5 and negative 2 really were solutions. The solutions that we find with this method really are the solutions to the original equation. But wait, we did something that we're a little bit suspicious of in this process. We multiplied both sides by a variable expression. We've been avoiding that so far. It seems like nothing went wrong this time. Why are we avoiding that again? In the next video, we're going to see an example where something goes wrong because of this move.